Welcome, Statistics 1 students, to week 16 of maintenance. The first question here is, all the questions are from a past exam, but what I have done with this first question is take out the drawing or sketching of the histogram. Obviously, if you wanted to sketch the histogram for this, you would need to, first of all, find the frequencies and then work out the frequency density. So I'm sure you all know how to do that, and I didn't want to waste too much time on that. So the first question we have here, so we've got these athletes running 100 meters, and we've got their times summarized in a cumulative frequency table, so it's important, cumulative frequency. We've got to state how many athletes ran a time of between 10.5 and 11 seconds. Now, because it's cumulative frequency, we probably want to convert these to frequency, so I'm just going to add a frequency column underneath here, so you can see that this one will be 6, and then from 10 to 40 is 30, and then from 40 to 49 is 9, and then from 49 to 57 is 8. So there's all of our frequencies in there, and that means that the one that we're looking at is, what are we looking at, between 10.5 and 11, so that's this category here, which is 6. So the answer would be 6. Calculate estimates of the mean and variance. Okay, so the mean, so for the mean here, I will take I probably need some mid-interval values, don't I really? So I'll put in my mid-interval values on top of this table here. We can ignore that one, I guess, because it's, well, I'll put it in anyway. 10.25. Next one is 10.75. Oh, hang on. No, I've got that wrong. Okay, I'll just start here. 10.25, because that one goes up to 10.5 from 10. So this one should be 10.75. The next one is 11.5. Whoops. I hate it when it does that. 11.5. The next one is 12.25, and then 13. Okay. So I guess if we're trying to find out the mean, we're going to go 4 times 10.25 plus 6 times 10.75. I hate it when it does that. Plus 30 times 11.5 plus 9 times 12.25. So we're just getting the sum of the data here, or an estimated sum of the data, plus 8 times 13. And we'll divide that by the frequency. Now, the total frequency, we've been told right at the beginning here, is 57 athletes, so we divide that by 57. Now, when I did this before, I got an answer of 11.7 to 3 significant figures, and of course I saved my unrounded answer into my calculator because I'm going to need that for the variance. So that's my mean. My variance is sigma squared, so this is equal to obviously the sum of x squared f over frequency minus the mean squared. Okay, so we can apply that over here. So we get 10.25 squared times 4 plus 10.75 squared times 6 plus 11.5 squared times, I think that one's 30, yes, 30, plus 12.25 squared times 9, plus 13 squared times 8. I pop that over the 57, and then I'm going to take away my mean squared. Now, I would use my unrounded answer here. It's not 11.7, it's actually 11.6 something or other, I think. So I'd definitely use your unrounded number there. And then when I pop that into the calculator, I'm getting 0.547 for my variance. So that's the representation of data question. Okay, so the next one we've got Roger and Andy playing a tennis match in which the first person to win 2 sets wins the match. The probability that Roger wins the first set, Roger wins first set is 0.6. For sets after the first, probability Roger wins set is 0.7 if he won previous set, 0.25 if he lost. No set is drawn. Find the probability there is a winner of the match after 2 sets. Okay, so for there to be a winner after 2 sets, we'd have to have Roger win twice in a row, or good old Andy has to win two in a row. Okay, so there we go. Now, what's the chance of Roger winning 2 in a row? Well, the first set is 0.6, and then if he won the first set, then there's a chance of 0.7 that he wins the next one. So this gives us 0.42. And then for the other chap, what's his face? Andy. Andy has a chance of 0.4 of winning the first match set, and then the chance of him winning the second one would be 0.75, because the chance of Roger winning it would be 0.25 if he loses the first set, so it must be 0.75 for Andy. What do we get there? 0.4 times 0.75. That's giving me 3/10, or 0.3. And then we just sum those together and we get 0.72 chance of the game being over after 2 sets. Well, that's nice. Find the probability that Andy wins the match, given that there is a winner to the match after exactly 2 sets. Oh, well, we've set up nicely for this. So we want the probability that Andy is our winner, given the fact that we finish the game after the second set. Second set finish. Okay, that's my attempt at writing this out in notation. So that means we want the probability of Andy winning intersection with the second set finish over the probability of a second set finish. Now, on top, Andy winning and a second set finish is 0.3, I think, wasn't it? That's what we found there. And the probability of a second set finish is 0.72, which we found out in the previous question. So if we pop that into a calculator, what do we get? I'm getting 5/12 as my final answer. That was nice and easy, actually. We've done all the work in the previous question. Now we're moving on to the discrete random variables. And so for this one, coin A is weighted so that the probability of throwing a head is 2/3. B is weighted so the probability of throwing a head is 1/4. And we throw coin A twice, and coin B is thrown once, and we've got to show the probability of it obtaining exactly 1 head and 2 tails is this. Okay, so how can we do that? Well, we've got coin A, and we're doing a double throw here, and then we've got coin B. So we could get heads, exactly 1 head. So we could get heads, tails, or we could get tails, heads, tails, or we could get tails, heads. I think those are the only options that we can have there. Now, looking at the first one, to get a heads, it would be 2/3, and then it's 1/3 to get the tails for coin A. And then we've got, now, what's the chance of getting a tails with coin B? It looks to be 3/4, since the head is 1/4. And the next one is just the same, except we're swapping the 1/3 and the 2/3 around. So it'll be that. Now the last one, we get 2 tails in a row with coin A, so that's 1/3 times 1/3. And then we're getting the heads with the second coin, which we're told is 1/4. So if we just sum all of that together, we should have the right answer here. And indeed, when you do add all of those together, you get 13/36. So you might just want to show that, work out the individual results and sum them together to prove that it's 13/36. I'm not going to waste my time doing that now. Okay, we've got to draw a probability distribution table for the number of heads obtained. Okay, so you're throwing the coin 3 times. You're tossing 3 times. So you could get 0 heads, 1 head, 2 head, or 3 heads. That's the only options that you have, and we've got to find the probability of x being equal to x. And so this is our little table here. Now we already have found out 1 head, so that's 13 over 36. And I hope you can see that 0 heads would be nice and easy, because you'd have to get no head on A and no heads on B, which is that. Now that gives me a total of 112. You can also see that 3 heads is easy because it's heads, 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 so it's 2/3 squared for the coin A, and then we've got to multiply that by getting a head for the coin B, which is 1/4. Now for that, I'm getting 1/9. And 2's a little bit more complicated, so let's just move this up here. Let's think about 2. Well, we could get, if we think about A, we could get heads, heads, and then for B we could get tails. Or we could get heads, tails, heads, or we could get tails, heads, heads. Those are the 3 options. Now to get a heads, heads, tails, that's obviously 2/3 squared times 3/4, because not getting a head is 3/4 for B. And then these 2 are exactly the same. They're just altering the order of the heads and tails for A. So we've got 2 lots of, what is it, 2/3 by 1/3 multiplied by 1/4. Now I sum all of that together, and when I sum all of this together, I'm getting 4/9. You can check that, but that's what I'm getting. Find the expectation of the number of heads obtained. Okay, so the expected value is what we're talking about here. It's going to be equal to 0 times 1/12 plus 1 times 13 over 36 plus 2 times 4/9 plus 3 times 1/9. Now, I'm getting, when I add this all together, I get 1.58 to 3 significant figures. Now, the next question here is a permutations and combinations one. We've got the school that has members from 3 different year groups. Year 1, it's a club, right? Year 1, 2, 3. And there are 7 members from year 1, 2 members from year 2, and 2 members from year 3. And 5 members are selected for the club. Or 5 members of the club are selected. We've got to find the number of possible selections that include at least 1 member from each group. Okay, so let's do this. Year 1, year 2, year 3. So I guess we could have 1 and then 2, 2. You can't have any more than 2 from year 2 and 3 because that's the maximum they have that are in the club from those year levels. So we can't do any more than that. Now we can move our year 1s to having 2 year 1s, which means we could either have 2 here and 1 there, because remember we're trying to add up to 5 in total from the club, or we could do 2, 1, 2. Finally, we could do 3 and then 1 of each. And those are the only options that include at least 1 member from each year group. Now, what are the chances of getting these? Well, so for this first one here, we're choosing from year 1, we're choosing 1 out of the 7 members. So that's simply 7 choose 1. And then we're choosing everybody from year group 2 and everyone from year group 3. So there's only one way of doing that. So that's 7 choose 1. The next one is 7 choose 2. Because you can see we're choosing 2 from that year 1 group. And then we're choosing everyone from year group 2. And then we're choosing 1 from the 2 options in year group 3. Now the next one, 7 choose 2, because we're choosing 2 from year 1. Then we are selecting one of the year 2 students, so let's choose one, and then we're selecting everybody from year 3. The final option is 7, and we choose 3 of them from group year 1, and then we choose 1 from year group 2, so that's 2, there's 2, we choose 1, and then we choose 1 from year group 3, which is 2, choose 1. Now let's multiply all of those together and add them up. So that one is 7. This one is, what is this one? Choose 2. That one is 42. This one is 42 as well. So I'm going to choose 3. 2 times 2. The next one is 140. Now if I add those all together, I'm getting 231. So 231 selections are possible. Okay, now let's move on to the next one. It's another permutations and combinations question. How many different numbers can be made from some or all of the digits of this number here? All 7 digits are used, and the odd digits are together. No digits are repeated. Okay, so we're making a 7-digit number. Let's look at our odd numbers. We've got 1, 3, 5, 7, and 9, and then so they've got to all be together, and then we've got 4 and 8 are our non-odd numbers. So you can see that if we're keeping these 5 together, you can hopefully see that we've got 1, 2, 3. So we go 3 factorial for rearranging there. But then within that, we've also got to rearrange the odd numbers. So we're going to rearrange them with 5 factorial. Okay? And so it'll be just simply 3 factorial times 5 factorial, which is giving me 720. You might be thinking, hang on, what about the 4 and the 8? Don't we rearrange them too? Well, yes, we do, and that's simply part of this 3 factorial. Okay, and for every one of those ways that we can move the odd numbers and 4 and 8 around, there are also 5 factorial ways for each of those, because we can rearrange within those 3 different options. We can rearrange the odd numbers within themselves. So the next question, the numbers made are even numbers between 3,000 and 5,000. Okay, all right, and no digits are repeated. Okay, so if they're even numbers, we can go 3,000 ending in 4, or 3,000 ending in 8. We're not repeating digits, so we can't. That limits things a bit. Or we could have 4,000 ending only in 8. That's the only way we could get an even number. Okay, now we're not repeating numbers, so what are the numbers left that we can use here for 3,000 ending in a 4? We could use 1, 5, 7, 8, and 9. Now, there's 2, and we're choosing from 1, 2, 3, 4, 5. So we could choose 5 from 2, and then once we have chosen them, there's 2 ways of arranging them. We could have them first or second position, right? So that's that lot. And I hope you can see that it's going to be exactly the same with this next one. So we'll have 1, 4, 5, 7, 9. So it's again going to be 5. Choose 2 of them, place them, and then there's 2 options for placing those 2 numbers. You know, for instance, if you chose 4 and 5, you could have 3, 4, 5, 8, or you could have 3, 5, 4, 8. That's why I've got this extra 2 here, right? Okay, the last one, what have we got left? We've got 1, 3, 5, 7, 9. So again, you've got 5, choose 2, and you can arrange them in 2 different ways. Now, 5 choose 2 times 2 is 20. And so you've got 20, 20, 20. So total 60 is the answer there. Now, the last number, we've got to make numbers that are multiples of 5 and which are less than 1,000. Okay, let's just bring this number down so we can see what it is. Okay, here's our number. Multiples of 5. So if it's a multiple of 5 and it's got to be less than 1,000, well, obviously we could have 5. That's the first one. So that's one way. And then we could do something like this, something 5, because you see there's no zeros there, so it's got to end in 5. Now, and we can repeat digits. So for this, you can see that there's 7 ways, right? Because there's 7 numbers here. We could have 15, 35, 45, 55, 75, 85, 95. So that's 7 ways there. Now, the next one, we could go with 100, and you see that there's going to be 7 ways there because we can put 7 digits in there. Then we can go to our 3s, so 3 something 05. Again, there's going to be 7 ways that we can do that because we've got 7 digits because we're allowed to repeat. We can go to 4, and you can see the 7 ways. We can go to 5, again, 7 ways. Right, because I could put a 515, 535, 545, 555, 575, 585, 595. Then we could go to 7, the 700s, and again we've got 7 ways. Then what are we're trying to be, well, it's got to be less than 1,000, so then we can go 8. We've got 7 ways there. I'm sure you can see the shortcut here, but bear with me. And then we've got another 7 ways there. So you can see that we've got 1, 2, 3, 4, 5, 6, 7, 8. We've got 8 ways of making 7. 8 ways of 7. So 8 times 7 here. And then we've got 1 here. So that is 57 ways, or 57 numbers that we can make that are multiples of 1,000. Okay, team. Well, I hope that's been helpful to you today. I hope it's making sense. And if you do have any questions, do let me know. Take care. See you later.